welcome to Sheldon Cooper Presents Fun with Calculus. My apologies that this episode is coming late. I did shoot one last week in honor of Teacher Appreciation Month, but I was informed by my roommate that my spot-on portrayal of Mr. David Finnerty could be considered wildly insubordinate. My heart goes out to the members of the NEA who, like me, have been kept down by the man. Now, let's talk about area and volume. First, let's take the area of a sine curve.
Hang on, Dr. C. A sine curve doesn't make a geometric shape. What formula will we use?
We don't need a formula because we have integrals.
Cool. I think I just learned something.
Did you have fun?
I'll say!
Now, taking the integral of a function is the same as finding the area under the curve. So if we take the sine curve and evaluate it from, say, 0 to pi, we can find the area. First, we'll start with the antiderivative, which is negative cosine of x evaluated from 0 to pi, which leaves us with negative cosine of pi minus negative cosine of 0, simplified to negative cosine of pi plus cosine of 0, thus giving us 1 plus 1 equaling 2 units squared.
Whoa! What else can we do with integrals?
I'm glad you asked, Amy. We can also use integrals to find the volume of a solid generated by revolving a curve about a line.
You mean like
This? Precisely. Let's use y equals x squared as our curve, and we'll revolve it about the x-axis to find the volume from 0 to 5. When you revolve an object, it creates a solid with cross-sectional areas that are always a circle, so we must integrate the formula for the area of a circle, which is pi r squared, where r is our function.
So you're saying that integrating a function gives you area, and integrating area gives you volume?
You got it! So let's set up the integral. Spread your legs. Invite them in. Now let's solve the integral. First, take the antiderivative of pi x squared squared, which leaves you with pi over 5 x to the 5th evaluated from 0 to 5, which gives us pi over 5, 5 to the 5th, minus pi over 5, 0 to the 5th, which simplifies to 3,125 pi over 5 minus 0, thus leaving us with 625 pi minus 0, leaving us ultimately with the answer of 625 pi units cubed.
That's super cool! But can we also revolve around the y-axis?
Gosh, Amy, what did you have for breakfast? A big old glass of good question juice?
Nope, just my Wheaties.
Well, we can absolutely revolve about the y-axis. Say we have our curve y equals x squared again, but this time you want to revolve around the y-axis. You must put the function into terms of y and integrate from y equals a to y equals b. Our new equation will be x equals the square root of y. Setting up the integral, we have pi times the square root of y squared dy evaluated from 0 to 5. Taking the antiderivative of that, we get pi over 2 times y squared evaluated from 0 to 5. That gives us pi over 2, 5 squared, minus pi over 2, 0 squared, which simplifies to 25 pi over 2 minus 0, giving us 25 pi over 2, or 12.5 pi units cubed.
Wow, Dr. Cooper, you sure know how to make calculus fun.
You bet your sweet A I do. Before we conclude this episode, I would like to announce the winner of our Solve That Equation contest. But I can't, because the only entry was from Matt Corn 15. And I would just like to point out that the letters F and U are variables not typically used together in calculus. Join us next week when we dive into parametrics. Now we'll solve the integral. Oh, crap.
Stupid technology!
But I was informed by my roommate that my spot-on portrayal of Mr. David Finnerty could be Cut. Start again.
Okay.
Which would give us no, we have to find the antiderivative.
my mom if she plans on being here much longer.
Sine of x, and take the integral of it from 0 to pi. That didn't work out at all. What the heck? Now take the integral of fucking. Gosh, Amy, what did you have for breakfast? A big glass of good question juice?
Nope, just my Wheaties.
We can absolutely revolve around the y equals x axis. Y equals x? No, that didn't sound right. About the y axis. Ready? Bring it up again. Bring it up again.
I'm going. You can blame all on me.
Come on.